Hi everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting the lecture 4 of Bode plots. So in the previous lecture we learned how to plot the Bode plot in a methodological step, right? We did a few examples, okay, one example only, and we also did the Bode phase plot and the Bode gain plot. Simply, Bode plot is basically the algebraic sum of all the individual blocks or components. But obviously we don't have enough time to plot them individually then add them up. So we want to do this in a very short manner. For that we'll obviously understand few steps, okay, but before that I gave you one point, that Bode plots can only be analyzed for minimum phase system. Okay, this is obviously conditional because there is one thing that we want to analyze from the Bode plots. That's why we only use it for minimum phase system. Obviously Bode plots can be plotted for non-minimum phase system as well, but from them we won't be able to get our desired information. What do I mean by that? We'll understand, but before understanding that we have to understand what are minimum phase system and non-minimum phase system. So first we'll understand these two, difference between these two. Why are they called minimum phase system? Why is this minimum term present and other things? Then we'll plot Bode plots for different functions. So what is a minimum phase system? For MPS is referred as minimum phase system and NMPS is referred as non-minimum phase system. For a minimum phase system, all the poles and zeros should lie on the left hand side of the j omega axis. Basically if we have a s plane and all the poles and zeros for a minimum phase system should lie on the left hand side. Okay, very important, should lie on the left hand side. Should lie on the left hand side. Okay, so this is the definition of a minimum phase system. Minimum phase system. Okay, so yeah, this is the definition of minimum phase system. Now let's understand with few examples that which one is a minimum phase system and which one isn't. So here all the poles and zeros should lie on the left hand side of my j omega axis. For like this is for the OL tape also, you can say OL tape also you can say. So here what do you have? So here any transfer function, this is not for like it is asking about the transfer function or something. It is telling us about any function you have been given as a function of s, and all the poles and zeros should lie on the left hand side of my s plane, so that like then it will be called a minimum phase system, else it will be called a non-minimum phase system. Now these are few examples, you try to solve it by yourself. Tell me, according to the poles and zeros, what is a minimum phase system and what isn't a minimum phase system. So I will solve this now. So let's solve the first one. So here if I see, let me draw the pole zero diagram directly. Sigma j omega. Oh no. So here like where are my pole locations? One of them is at -1 and another one is at +3. So -1 and +3. Okay, where are my other pole locations? So other pole location is here, like this is 0 location, which is at -2. So we have another 0 at -2. Okay, so pole 0 pole, so these are my locations. So is this a minimum phase system or non-minimum? This is a non-minimum phase system, as one of the poles is lying on the right hand side of my j omega axis. This is a non-minimum phase system. Now what about my second? So I will just copy this one for the second and third one. So this is g2 of s. So here where are the location of poles and 0? One is at poles are at -1 and -3. So -1 and -3. Okay, and here where are my zeros are at -2, s equals to -2. So in between these two, zeros are at -2. So this is this is a minimum phase system, because I don't have any pole or zero on the right hand side of my S-plane. Okay, just like that contour thing, right? Nike's contour thing. So nothing is on the right hand side, everything is on the left hand side. So yeah, this is a minimum phase system. Okay, like you might say, then what is the difference between, like you can say this is a stable system, like minimum phase system or stable system? Yes, they are stable system, but what is the difference between like stable system and this one is that for the condition like stability condition, none of the poles should lie on the right hand side of my S-plane. But here for a minimum phase system, none of the poles and zeros, both of them can't lie on the right hand side of my S-plane. So both of them can't lie. There for stability, it was only like the condition was only for the pole. Here the condition is for both of them, poles and zero itself, for minimum phase system. Okay, let me just check if everything is recording. Yeah, everything is recording fine. Okay, so let's go to the third system here. Let's go to the third system. So here you will see the difference. So these here we can say this is a stable system. Like if this is a CLTF of a system, closed loop transfer function system, then we can say this is stable system, this is unstable system. So you can deduce from here that yeah, unstable system are non-minimum phase system and stable system are minimum phase system. You can deduce from here. But let's go to the third example, and from there your misconception will get cleared. So here we have a 0 at s equals to 2, 0 at s equals to 2. So 0 at s equals to 2 and pole at s equals to -1 and pole at s equals to -3. -1 and -3. Okay, s equals to 2, -1 and -3. Okay, so these are the things. Now is this a minimum phase system or non-minimum phase system? This is a non-minimum phase system because one of the zero is lying on the right hand side of my S-plane. But is this system stable? This system is stable. Like if let's say assume that this is a closed loop transfer function, the pole zero diagram of a closed loop transfer function, then you can safely say that this system is stable because all the poles are lying on the left hand side of my S-plane. But this is still stable, but still it is not minimum phase system. It is non-minimum phase system. It is not a minimum phase system. So this system is NMPS, but stable. Here and stable. So you can say, like if a system has a transfer function like this, and if it is a minimum phase system, you can safely say that it will always be stable. But converse won't be true. This is not stable. Okay, non-minimum phase system can be stable as well as not stable. Okay, both of them can happen. So what I can write here is that if CLTF of a system is given, okay, it is not that important point, but still few things you can like deduce from here, right? That's why not that important point I'm writing here. CLTF system is given and it is minimum phase system, then surely it will be stable. The system system will be stable. Okay, very important. System will be stable. But vice versa is not true. But converse may not be always true. Okay, so yeah, this is about the minimum phase system and non-minimum phase system, basic definition. Now, why is this called a minimum phase system? Like you might like the question may arise, it can be called anything else, like no pole, zero right hand side, like that. But why is this called minimum phase system? Let's understand that. Let's consider we have a two stable systems we have. Okay, like one of them is non-minimum phase system and one of them is minimum phase system. Okay, here all the poles and zeros are lying on the left hand side, and here one of the poles and zero lying on the right hand side. One of the zero is lying on the right hand side. So we have two systems. Now one more thing we have to assume is that these coefficients tau 1 and tau 2 are obviously positive. Tau 1 and tau 2 are obviously positive. This is the another thing. Okay, now let's write the angle expression for both of them and the magnitude expression for both of them. So g1 of j omega is equals to this 1 plus j tau 1 of omega plus 1 j tau 2 of omega. Okay, now what is g2 of omega? g2 of j omega equals to 1 plus j 1 minus j this time 1 minus j tau 2 of omega 1 plus j, okay, this is tau 1 actually, tau 2 of omega. So these are the two things. Now what is the magnitude? g2 of j omega equals to 1 plus tau 1 omega whole square divided by 1 plus tau 2 omega whole square. So this is g1 actually, sorry. And here this will be also same because it is getting squared, so the magnitude will remain same. What about my angle? What is happening to my angle? So angle of g1 of j omega is simple. All of them are coefficients are positive, so no issue. Normal method we will use, which is tan inverse tau 1 of omega minus, now this is due to the 0 and let's do it due to the pole, so we'll just reduce the size of this one, tan inverse tau 2 due to the pole this is. Okay, now what is angle of g2 of j omega equals to angle of g2 of j omega equals to this tan inverse. Now here what is happening, my y is negative, y coefficient is negative and x is positive. So which quadrant I am lying? So this angle condition, right, angle concepts will always come up, so be crisp with those concepts. So here this y is positive and x is y is negative and x is positive. So x is positive and y is negative. I'm lying around here in the fourth quadrant. So what will my angle be? Angle will be minus tan inverse theta, minus tan inverse omega tau, right? Minus tan inverse omega tau. So this will be, due to the 0 I am getting minus tan inverse tau 1 omega, and due to the pole what I am getting? Due to the pole I am getting minus tan inverse tau 2 omega. So minus tau 2 omega. Okay. So these are my two angles. Now what do you observe is that angle is different. Okay, angle is different as the sign was different, but the magnitude was same. Magnitude was same because we're squaring here. We're squaring. So here at omega equals to 0, what is my angle? So let me just reduce, like write in small letters. Omega equals to 0. My angle is g1 of j omega. At omega 0, my angle is simple 0, and at omega, here at omega equals to 0, my angle is here also 0. That is fine. My angle is here also 0. Okay. But what about my omega equals to infinity? What about my omega equals to infinity? So at omega equals to infinity, what is happening? Infinity, angle of j omega equals to infinity equals to what? So this is tan inverse infinity. Tan inverse infinity is what? 90. 90 minus 90 is 0. So I am going to 0 itself. But here what is happening? G2 of j omega at omega equals to infinity equals to what? Here if you do tan inverse infinity, here it is minus 90 and again minus 90. So minus 90 minus 90 is minus 180. So overall angle I am getting as minus 180. So here the angle is different, like any angle is different. Okay, one is going to 0 and another one is going to minus 90. Okay, so this is the basically the phase plot for both of them, and here I have shown one parameter, like this is for g1 of j omega and this is for g2 of j omega. So what we observe here is that one parameter we observe is the maximum change in phase, maximum distance from the 0 degree angle. Okay, maximum distance from the 0 degree axis. So here for this one we get del phi 1 equals to 90 degree. Maximum we can go to, no, okay, not 90 degree, sorry, this is at max what we can go. You can differentiate this one. Okay, depending upon this one you will understand. So obviously that will be something less than 90 or less than 40, I don't know exactly. Okay, but this is the max I can go. Obviously I won't be able to ever reach 180. That is impossible for me to reach. Okay, so I don't know what this value will be. Okay, let's name this as delta phi 1, whatever. Okay, so yeah, let's name this as phi 1 anyways. So this is the maximum or you can say the minima that it can get, minimum. Now this is going even, this is going at max 180. So here what is my delta phi? It's delta phi max. This, let's say this is delta phi max. Okay, delta phi max of 1. Okay, and this is delta phi max of 2. So now what is happening here? So what I can observe is delta phi max of 2 is 180 degrees maximum, like the distance between this axis, and this is maximum distance is this delta phi max, which is phi 1, let's say. So this distance will be always less than this distance, right? Hence, that is why we call it a minimum phase system. That is the only reason, no other reason. The two systems are same, but the distance from the this omega axis is least for this one. Hence, it is called as a minimum phase system or minimum distance. Okay, minimum distance you can call, like analogy you can get. So here, as I can say, you don't have to understand, this is just the theoretical part. Even if you don't understand, don't worry, this won't come in gate examination or something. This is just a theoretical part that I wanted to tell you. Okay, mainly you have to solve numericals, so like this isn't coming under numericals, but still few people want to get a brief idea about this one, so that's why. As distance, that's the maximum distance. It is called, this is also another definition, minimum phase system. I will just write MPS, okay, and you try to like understand the full form. What is happening? Okay, this is known as the minimum phase system. Now, like why do we only draw Bode plots for minimum phase system? We understood like what is a minimum phase system, what is defined by minimum phase system, what is defined by non-minimum phase system, and the difference between those two. Now, why we only draw for minimum phase system? Let's understand that. So let's take an example. So again, I have two transfer functions. One is g1 of g1 of s. So g1 of s equals to one plus s tau, and g2 of s equals to 1 minus s tau. Okay, they have the same magnitude, but the phase angle will be different, and obviously one is minimum phase system and the other one isn't. So let's find the difference. So magnitude will be same. Okay, I'll just write them directly here, won't waste any time. So this is under root 1 plus omega tau whole square, and here g2 of g omega one plus omega tau whole square. Okay, so magnitude are same. And then what is the next thing? Next thing is like let's do this in Bode plot. Simply this is what this slope of minus 20 p per decade. Okay, this we know. So this is minus 20, already we know this, minus 20 log under root 1 plus omega tau whole square. Okay, and this is looking like a square, but this isn't a square, trust me. This is more of a tau. Here also it is same only. So magnitude is same. Now what about my phase angle? What about my phase angle? So what about my phase angle? So phase angle here, it's basically g1 of g omega. g1 of g omega. So what is my phase angle here? Phase angle for this one is minus tan inverse omega tau. Minus tan inverse omega tau. Okay. And what about the phase angle of this one? g2 of g omega is equals to this one. Now what is the phase angle of this? You remember, right? Your now y is negative and x is positive, so what will happen? Minus tan inverse, and it's in the denominator, so obviously minus minus it goes above, so minus minus becomes plus tan inverse omega tau. So this time I won't explain this in brief. So like I hope you already know all these things. Plus tan inverse omega tau. So phase is just the opposite. They are going the opposite direction itself. So here if they are going the opposite direction, what does this mean? So it will be like this. So one of them will have the, both of them will have the magnitude plot same, right? Both of them will have the magnitude plot same. So if I draw the magnitude plot, okay, let me just write the phase later on. First let me write the magnitude characteristics. So if I draw the magnitude plot for both of them, this is omega and this is magnitude of g1 of j omega. It will be simply like this, like it will start from 0 dB. Okay, like this is not 0 dB, don't worry, it will start from 0 dB and it will hit the corner frequency and it will reduce by slope 0 dB, 20 dBs per decade. So minus 20 dBs per decade, start from 0 dB, this is 0 dB, okay, and this is the corner frequency, and the g2 of j omega, magnitude of g2 of j omega will be just carbon copy of this one, ditto, because the magnitude are same. So here if I just copy and paste, okay, I will be shameless, just copy and paste this one, I'll just reduce the size of this one. I'll just change this to g2 of j omega, okay. So this is my g2 of j omega and this is my g1 of j omega. Now they are same. What about my phase? So phase is just different. So like from here, like as I told in the starting of previous lecture, that what type of questions we solve. The questions we solve is we have to recover the transfer function by just seeing the Bode plot. Maximum questions come from this topic, that you have been given this magnitude Bode plot and you have to tell what transfer function is this. Now you have been given this two magnitudes plot. Can you tell me which one is which transfer function? Which one is g1 of j omega and which one is g2 of j omega? Obviously it is written over here, you can tell. But if the two transfer functions same are given, magnitude plot are given, can you tell me which one is g1 of j omega and which one is g2 of j omega? No, you can't. No, you can't. Right? No, you can't. That's why we have established a rule that we will only plot for minimum phase system, so that if this magnitude plot comes up, so I can have only one transfer function according to this magnitude. So if I am only plotting for, like, information is known that I am only plotting for minimum phase system. So if I am only plotting for minimum phase system, the transfer function of this one will be only this one, okay, unique connection, right? Else if we don't know if like we can plot for both minimum and non-minimum phase system, then I wouldn't be able to tell what does this magnitude plot represent, like which transfer function does this magnitude plot represent. Here this represent this also and this also, right? These are same only, so I won't be able to tell. So obviously we can draw Bode plots for non-minimum phase systems as well, but while recovering the transfer function from Bode magnitude or Bode phase plot, we won't be able to recover, as we won't have a unique relation, okay, as this one can have two transfer functions, this one also, okay. I won't be able to tell which one is which one, okay. But if it is known that we will only plot Bode plot for minimum phase system, then for sure the transfer function of this one will be only this one, because only minimum phase systems are allowed, non-minimum phase systems aren't even allowed, okay. So that is the reason, that is a simple reason. Obviously if you do the phase plot, you will see that they are opposite to each other. If you do the phase plot, you will see that they are opposite to each other. So that's how we can identify. So here just draw the phase plot. If both of them are given, then only you can identify. If either one of them are given, you won't be able to tell. So omega So how is the phase plot? So phase plot will be something like this: 0, then like this, then like this, okay, 0 degrees. This is minus 90 degrees. And what will the phase plot? This is 90 degrees. Okay, now you might say, sir, here the distance isn't minimum between these two. Yes, it is true. The distance for this one is like the same, but like even they are same, then also you can tell this as minimum. Okay, don't go to the particular definition, but just for the confusion I want to clear. So if you know the phase plot of both of them, you will be able to tell. But generally what will happen is you have to find the transfer function from the Bode magnitude plot only, from the Bode gain plot only, and they won't give you the Bode phase plot. Okay, so if both of them aren't given and only Bode gain plot is given, obviously you won't be able to tell. Okay, unique response won't be able to tell. Okay, that's why we don't plot for minimum phase system. So for minimum phase system, we can determine transfer function from Bode plot either by using magnitude or by phase plot. So if we know that this like we are plotting Bode plots for minimum phase system, so we will be able to identify the transfer function from either the magnitude plot or the phase plot. Okay, but for non-minimum phase system, we need both magnitude and phase plot to transfer function. Now engineers are very lazy, so they want as little information as possible. Like from the engineers want to what do you say, engineers want to give out as much more information as possible from as little information present as possible. So just from the magnitude plot they want to say everything. Okay, they want to find the transfer function. They don't want both magnitude and magnitude and phase plot. Okay, so from as little as information as possible they want to give out as much as possible. So that is known as efficiency, right? So yeah, that is why basically we don't have both of them, we have only one of them, and through one of them we want to give more information. So to give more information, we will only be able to determine for minimum phase system and for not for non-minimum phase system. So this is an important point. Now how to draw Bode magnitude plot? How to draw Bode magnitude plot? So like this is coming to the steps. Okay, these are the steps. Basically we have already done it actually, but these are well written. So if even if you forget something or something, you can come back to these notes and you can again revise like how we draw the Bode plot. So previously what we are doing the algebraic sum, we won't do that. What we will do, obviously we will replace s by g omega for the given function to convert it into frequency domain. That we anyways do in polar plot also, Nyquist plot also. Then convert it into general time constant format. What is general time constant format? This is a general time constant format. So this has already been covered in lecture 1, or not lecture 1, in chapter 1, but again I'm revisiting this one. So general time constant format is like this. So here there will be coefficient of s, and like the summation terms of s will be 1 only. All of this will be 1, and these are the time constant, right? Tau 1, tau 2 are the time constant. And what are the corner frequencies? Corner frequencies are 1 by tau 1, 1 by tau 2, and 1 by tau 1 dash, tau 1 tau 2 dash. All these are corner frequencies. Okay, so this is the general time constant format. I'm not going much in details of this one. Okay, so yeah, this is there. Now then you find the d-secant and you write the d-secant expression, right? From where the Bode plot will start. Okay, that magnitude d-secant you write as you know the d-secant. From if you put s equals to 0 over here, you will get the d-secant as k, or simply you put s equals to 0, there also you can get d-secant. Okay, don't need to convert it into general time constant and find the d-secant if only that is required. Simply put s equals to 0. Now identify the corner frequencies. So these are the corner frequencies, right? So after converting into general time constant format, the corner frequencies will be something like this. Okay, 1 by tau 1, 1 by tau 2. Then do the algebraic sum of slopes of each corner frequencies depending upon the number of poles and zeros. Okay, that we have already done, the table that I am talking about. So here we'll try to solve it much more quickly so that you will understand, right? So like depending on the corner frequency, so the slopes we will add. Okay, those will be very simple. That's why Bode plots are very simple, because you can plot the frequency response in just matter of seconds. Okay, so yeah, let's do few examples and from there we'll understand further. So here let's do the first one. We're going to draw the Bode plot for this one. How do you draw that? So first you convert this into general time constant, s equal to j omega you do, but yeah, s equal to j omega you can put, but before that I will convert it into general time constant format. So yeah, sorry, I should actually do this first. Yeah, this one, right? This one should come before this one. Okay, so what you do is you take common 3, s plus c, which is equal to g of s. So this is 5 by s plus 3 plus 1. Okay, so this is a general time constant format. Now from here you can understand the dc gain. What is dc gain? Dc gain equals to 5. Now in dBs is 20 log base 10 5. I'm not interested in the exact value, so I'll leave it like this. Now this is from where my border plot will start. Okay, so generally what we do is we start our border plot from 0.1 frequency itself. Okay, so that is a general convention, nothing fixed is there, so it depends upon you. And just remember, this is log scale, don't forget this one. And magnitude g of j omega in dBs. Okay, now we are starting from this point. So this is what? This is 20 log 5, and we have a corner. What is the corner frequency here? We have only one corner frequency. What is the corner frequency? It is what you can say, like 1 by tau. So 1 by 3, 1 by 1 by 3, which is 3, or you can say directly the whatever is in the denominator of this s term. Whatever is in the denominator of this s term is the frequency, corner frequency. That also you can tell. So 3 radian per second. Okay. So here it increases, and then we get a slope. Where do we get a slope? We get a slope here at 3 radian per second. Okay, and what is this? What is this slope? This slope is minus 20 dB per decade. Okay, and here the slope is 0 dB per decade. Before corner frequency, we don't have any slope. We don't even have to use the table for this one. In most cases, you don't have to write the table for Bode magnitude plot or the gain plot. You have to draw the table for the Bode phase plot. So in this case, as we have only one corner frequency, it is very simple. We don't even have to draw the table for the Bode phase plot also. When there are more than 2 volts, then it becomes a bit hectic. So hence you have to draw the table. Okay, for the first one is very simple. So simply what you can do, we can plot the Bode phase plot. So you can see that, observe that how much time it took me to plot the Bode gain plot. Okay, here also you can say that, like, where will it cross the 0 dB axis, that all these things also you can say. How? Like, if in this question you have to find the what unity gain frequency or omega gc, gain crossover. So what will happen? Can you find that? Let's find that. So here this frequency is omega gc. Okay, let me write, just wait a second, let me drink a bit of water. Yeah, so this frequency is omega gc. This frequency is omega gc. So if this frequency is omega gc, what does it mean? So, like, can you find the omega gc? So we will use the slope formula. So what is, so let's name these 2 points as a comma b. This is a and this is b. So what is the slope? I'm just doing slowly for you guys. Okay, slope ab equals to yb minus ya divided by what it was in the formula, xb minus xa, and x is log 10 of omega b minus omega a. So it is basically log 10 of omega b by omega a. As they are in subtraction, they will come in division. So what is my slope ab? Slope ab is minus 20. Slope is minus 20 constant. Slope is minus 20. And what is yb minus ya? Yb is this, and what is yb? Yb is 0 dB, because this is the unity gain frequency. So unity gain means log 20 log 1 base 10. 20 log base 10 1 is 0. So in dBs it is 0. Minus ya. What is ya? 20 log 5. 20 log 5 divided by, this is log base 10, I should write. and this is log 10 of omega gc divided by omega a. What is omega? Omega is 3. Omega a is 3. This will come out to a bit weird function, so yeah, just bear with me. Okay, so this 20 minus 20 minus 20 gets cancelled, so here we have log base 10 of omega gc by 3 equals to log base 10 of 5. Okay, so simply what we can do, so these are all log based 10, right? So obviously this 5 should be equals to omega gc by 3. Okay, or you can simply raise to the power 10 both of them and you will get the same answer. So what do we get? Omega gc by 3 equals to 5 itself. You get omega gc equals to 15. Okay, this is the answer. 15 radian per second. 15 radian per second. Now is this the correct answer? Is this the correct answer? So let's put 15 over here. Let's put 15 over here. So if you put 15 over here, what do you get? So here, like this is j omega, so 15 is j5 plus 1. So it's almost like, if you do the magnitude, it is under root 26. So under 26 is almost 5. So 5 by 5 almost equals to 1. Almost equals to 1. So yeah, this is a correct approximation. Correct approximation. So yeah, from there also you can cross verify whether you're correct or no. So this is how you find the omega gc. Like this is how you find the parameters. So slowly I am going to that phase also. Okay, slowly I am going to that phase also, that how to find the different gain parameters. So we have already studied this in polar plot. Here also we can find the different gain parameters. Okay, so without even plotting the polar plot. So now let's plot the phase plot. J omega. So here what is the condition for phase? So condition for phase is simply like we have to draw for the 10 times before the corner frequency and 10 times after the corner frequency. So what is my corner frequency? Corner frequency is this 3 radian per second. So 3 radian per second will lie here, and 10 times before this and 10 times after this. And from where it is starting, that at omega goes to 0, obviously this gives 0 phase. Okay, this is positive, so this is 0 phase. At omega goes to infinity, this is dominating, so this will give me minus 90 phase, minus 90. So it will be something like this. Initially it will give me 0 phase. Okay, then we have a slope of minus 45 degree per decade, then it goes to minus 90. Okay, this is minus 90 and this is 0 degree. Okay, what is this? This is minus 45 degree per decade slope. Okay, minus 45 degree per decade slope. This is 0 degree per decade slope, this area, and this area is 0 degree per decade slope. Now from here, can you tell me the what, like the phase, like gain crossover frequency we have found out. Okay, gain crossover frequency we have found out. Now can you tell me the phase margin from here? So it is 15, so I am lying somewhere around here. Okay, lying somewhere around here. Okay, so you can find the phase margin. So what we can do is, so yeah, this is a bit difficult. Okay, we'll try. So we're just doing it on the go. So my omega gc is lying somewhere around here. Okay, it is 15, like not exactly between, because this will be more nearer to this, okay, or I don't even know the scale. Is it like 10 times this? So it won't be half, it will be something like this. I think it will be something like this. Yeah, so omega gc is here. Now can we find our phase margin? So for phase margin we have to find the phase margin was what? It was 180 plus angle of g omega at omega equals to omega gc. Okay, so here how do I find this one? Simply what you can do, again you can mark these points as this point as c, this point as d, and this point as c. Okay, so I know the slope in this region is minus 45 degree per decade and the angle is 0. and I have to find this angle. Okay, we don't know this angle, so this is t, this is okay. We have to find out this angle. So how to find out this angle? So I'm just solving some question. Okay, this is also a question, very good question this is. So now, so again, slope CD, slope CD will be what? Slope CD will be y of d minus y of c divided by log of 10 omega d by omega c, which is omega gc by what? 0.3. Okay, this is omega c, which is 0.3. So what is slope CD? It is minus 45. And what is yd? Yd we have to find out. So it is simply like name this as yd itself. Okay, what is yc? Yc is 0. Yc is 0. Okay, here yc is 0, c is 0, and this is log of 10 omega gc. What is omega gc? Omega gc is 15 itself. Omega gc is 15. So 15 by 0.3 is 550. So 550. Okay, so what will my yd be? Yd will be simply minus 45 log of 10 into 50. Obviously I don't know the value of this. Okay, what you can write is, it is simply minus like 45. You can break this down. Okay, I won't break this down. So this is the value of my angle. So what will my phase margin? I am not interested in obviously calculating this. So my value will be 180 plus 180 minus this 45 log of 10, 50. Okay, so this will be my phase margin. So from here you can also calculate the phase margin and gain margin. So gain margin can you calculate? Is it ever reaching my crossing the negative real axis minus 180 degrees? No, this is never crossing the minus 180 degrees. So gain margin obviously I won't be able to calculate, or phase crossover frequency also I won't be able to calculate. But gain, crossover frequency, and phase margin I will be able to calculate from these two parts. This was just the basic example of these two, right? Just a basic example. How can we find the gain margin and phase margin from the Bode plots? So this is the phase plot. Phase plot I have got the point that 10 times before the corner frequency and 10 times after the corner frequency, the slope will be minus 45 degree per decade. But after 10 like this 30 and before this 0.3, so 10 times before, sorry, what do I mean? Yeah, what do you mean by that is, now before this frequency the slope will be 0, and after this frequency the slope will be 0. Okay, in between the slope will be minus whatever degree per decade. So yeah, this is the main thing that I wanted to explain here. So this slope will be 0 degree per decade and 0 degree per decade. Okay, these slopes will be 0, right? Now let's solve for the second question. So this is the second question. Okay, so this is the second question. So what is the second question? So basically this is 2 by 3, and like let's first convert into general time constant format. So I take common 2 and 3. This is s by 2 plus 1. This is s by 3 plus 1. And this is s plus 1. Okay, so what corner frequencies I have? So for this also, like for magnitude plot also, we don't need to do what? We don't need to draw a table. Okay, we don't need to draw a table because simple. This is magnitude plot is very simple. Okay, so still I will draw a table because like we are just at beginner level right now. So we'll draw the table. We'll use the table from the previous example. Okay, it was way back. This is the table of slopes for. Okay, let me copy this. Reduce the size. Okay, and what are my slopes? So I'm starting from what, this omega equals to 1. So here I have pole, so I'm starting from this 1, then this 2, then this 3. So before this 1, obviously I don't have anything, so I should write this like this, that I did one thing wrong in the previous lecture, that I should have written it like this. So this is the range between 1 and 2. This is the range where less than 1. Okay, I should write this like this: omega is less than 1, and here omega is between 2 and 1. Here omega is between 3 and 2. Here omega is greater than 3. So these are my 3 ranges, right? So these are my 4 ranges basically. So initially what is happening, omega less than 1, we have nothing, right? Omega less than 1, we have this constant value, so magnitude is constant, slope is 0. Slope is 0 basically, slope is 0, and we have some magnitude. Okay, now after that we reach one pole. Okay, we reach one pole is reached. So let me just write the poles and zeros so that you will be able to easily identify them. So omega p1 equals to 1 radian per second, omega p2 equals to 2 radian per second, omega z1 equals to, sorry, omega p2 is 3, omega z1 is equals to 2 radian per second. Okay, so this is the case. Now what do you do? Now like we reach one pole at omega is to 1, so obviously I will get a slope of minus 20 per decade. Then what happens between 2 and 3? 2 I encountered is 0 after 2, okay, onwards. So obviously my slope will again be added to plus 20, so minus 20 plus 20 becomes 0. Then after this 3, what is happening? After this 3, I am encountering another pole again. So if I am entering another pole, so pole plus 0 plus pole, it becomes minus 20 dB per decade. Okay, simple only. So this is a table of slope. So again, this is like the previous case only, ditto copycat. So here omega magnitude of g omega in dBs. Okay, and from where is it starting? It is starting from this 20 log of what, 2 by 3, 2 by 3. So it is something negative, like as this is less than 1, so obviously log of something less than 1 will be like less than 10. Obviously log of something less than 10 will be negative, because the base, like anything less than the base will be negative. Okay, so after that, like let me mark the corner frequencies. This is 1, 2 and 3. So between 1 and 2, my slope is what, my minus 20. Minus 20. After that, its slope becomes 0. After that, what is happening? Again, my slope becomes minus 20 again. After 3. Okay. So yeah, this is minus 20 dB per decade. This is minus 20 dB per decade, and this is like 0 dB per decade. This is 0 dB per decade. Here the slope is. Okay, here the slope is 0 dB per decade. So yeah, this is the Bode magnitude plot. Now let's plot it for the Bode phase plot. So nothing to explain here, okay, nothing to explain here, as like this has already crossed like negative. This is never crossing the 0 dB axis. We can't find the gain crossover frequency because this is never crossing the 0 dB axis, because 0 dB axis is lying somewhere here above this, and this is negative already, okay, that's why. And this is always going in the downward direction. So this is it. Now let's plot for the Bode phase plot. So for the Bode phase plot, what we'll do is let me first copy the table of results. Like table of slopes. Okay, so this is the table of slopes. Now let me like mark the corner frequencies. So first let me write the zeros and poles. So let me reduce the size. What are the important points? So whenever you're doing this, right, and you have multiple poles and zeros for Bode phase plot, what is happening? Why can't I resize this one? Yeah. So whenever you have been given multiple poles and zeros and you have to draw the Bode phase plot, what do? You write the ranges down. So what do you know? Like omega 0, the effect of omega 0 will be valid 10 times before and 10 times after in this range. So this corner frequency. So effect of this omega z1 will be valid for, let me write here, 10 times before and 10 times after. Omega z1 10 times before and 10 times after. So 10 times after is this 10 times after is this 20, and all these are in radian per second. I'm not writing this. All these are in radians per second. 20 and 2. 20 and 2. Okay. Now what about the poles? Poles. So the poles basically here, like it is 0.3 and 30. The first one is 0.1 and 10. 0.1 and 10. And this one is, sorry, this is actually 0.2, sorry, like 10 times before, right? 2 divided by 10, 20. So this is the second pole I'm talking about. The effect of them will be valid in this range, right? For 0.3 and 30. All these are in radian per second. So I have written down the like ranges for which the effects will be valid, right? Like the slopes. I hope you remember, right? Slopes will be valid 10 times before and 10 times after, between that range. Now let me write here. The ranges. Okay, so I will write here the ranges. So basically, first, what is the least one? Least one is 0.1. So before 0.1, we have nothing, 0 degrees, right? Because k is positive. Obviously, this 2/3 is positive. So we have nothing. 2/3 is positive. Hence, before omega less than 0.1 is what? 0 degree. Other slope is 0, and also the like angle is also 0. Okay. So nothing we have. So I will just reduce all this, like delete all this. 0 degree, 0 simply. Now after, okay, let me just increase the size because this has reduced too much. Now after this, what is happening? Like now, what is the next least range? 0.1, and what is the next least one? 0.2. Okay, nothing is lesser than this 0.2. So I will write the range as omega is between 0.2 to 0.1. To 0.1. Okay, so this is one case. Now this is about this one. Now what about the overall slope? So now the overall slope, basically what we can say is here the overall slope will be what? Now whose effect is coming into effect? So this pole has just come into effect because my frequency, the range I'm lying is greater than 0.1. But this 0 hasn't even come into effect because after 0.2 it will come into effect, and this one will come into effect after 0.3. So only the effect of this pole is coming. So what will be the slope due to pole? Minus 45 degree per decade. Minus 45 degree. Let me do this in green. Okay, only due to the pole. Only due to the pole. Okay, I think we have already done this. The result will come same only. So now again, what is the next least range after this 0.2? Next least value is 0.3. So obviously I will vary from this 0.2 to 0.3. 0.3. So if I vary from 0.2 to 0.3, what happens? If I vary from 0.2 to 0.3, basically whose effects are coming to play? So these, like this is, yeah, we are in this range. It is less than 10. So yeah, it is less than 10. So effect due to this pole will come. Will the effect due to this another pole will come? No, I haven't still crossed 0.3, so this effect won't come. The effect due to the 0 will come now. So this will contribute a plus 45 degree per decade slope, and this will contribute a minus 45 degree a decade slope. So obviously overall slope I will get as 0 because pole and, okay, I will just write here. Okay, now next least range is after 0.3. Next least range is 10. Okay, next least range is 10. So we'll vary our omega from 0.3 through 10. So if you vary your omega from 0.3 to 10, what do you get? So here 0.3. So this is like, yeah, this pole is coming into effect now. 10, yeah, this pole is also still in effect, and this 0 is also still in effect. So all the three things are in effect. So what will my angle? Angle will be minus 45 because plus 45 minus 45, 0 minus 45. So overall I will get minus 45. Omega P1, omega P2, and omega Z1. Okay, now next our omega is varying from, what is the next least range? 20. So as we move greater than 20, this effect of pole is gone. So after 10, effect of pole is gone. So I will write heading so this is minus 45. Now what is next happening between 10 to 20? What is happening? 10 to 20, effect of this one is gone, only effect of these two are present. So again my slope will become 0. Again my slope will become 0. Take this one bit above, take this one a bit above, take this one a bit. Slope will become 0 as the effect of only this P2 and Z1 is coming. Okay, next, what are the cases? Next we have next least range is 20 to 30. 2030. So like this I can take a bit above. Obviously now what is happening? This effect of this 0 is also gone because it was valid only till 20. Now effect of this pole will come. So this effect of this pole will come. Obviously this is minus 45 degree per decade. Okay, so this is minus 45 degree per decade. This will be only due to the pole. Okay, after this obviously the effect of this pole will also become greater than 30. So everything will become 0. So yeah, start from 0 and so ends to 0. Let me just become very congested towards the end. So yeah, these are the basically location of the slopes. Okay, I hope you got the point. This is almost similar to the previous case, or if I don't remember. So let's now plot for the Bode phase plot. So initially my angle is 0 degrees. Initially my angle is 0 degrees. So it starts from 0. Let me mark the important points. What are the important points? These are the important points: 0.1, 0.2, 0.3, because every at this points the slope changes. So I have to obviously plot all this, right? So here the important points are 0.1, 0.2, 0.3, then 10, 20 and 30. Okay, these are not linearly scaled because this will be somewhat more closer to this, and this will be also somewhat more closer to this. Okay, so what is happening here? Now this is 0. Now at point 1 to point 2 I have a slope of minus 45. Okay, now after this, from point 2, what do I have? From point 2 to point 3 I have slope of 0, so it will be constant. And from point 3 to 10, from point 3 to 10, what I have slope of minus 45, slope of minus 45. Okay, yeah, I can do it better, yeah, like this. And after 10 to 20, what do I have? Again, between 10 to 20 I have 0 slope. Again this will be constant. And again from 20 to 30 I have slope of minus 45. Okay, if I can reach there somehow. Yes, I can. Yes, fine. Okay, after this my slope becomes 0. Now can you tell me what is this ending value? Can you tell me this? Can you tell me this? So the ending value here will be what? Minus 90. Why? Because you use that formula, minus 90 to n minus m. How many poles I have? 2. How many zeros I have? 1. 2 minus 1 into minus 90, which is minus 90. So overall I will move my minus 90 itself. Okay, this will be minus 90 and this will start from 0 degrees. And these are the slopes: minus 45 degree per decade. Again this is minus, this is 0 degree per decade, this is 0 degree per decade, this is 0 degree per decade, this is minus 45 degree per decade, this is again minus 45 degree per decade, and this is 0 degree per decade. Okay, so these are the slopes of different places, and this is minus 90. Okay, so yeah, now the third question what I will give you is, like, we have already gone few higher time, so I will draw this, but this is homework for you. There is twist in here. We have a square term here, so just be careful how to use the square term. What happens to the slope if you have like two poles at the same location? What happens to the slope of that corner frequency? Okay, and for the phase also. So I'm giving you homework for this 9th question, the Bode gain and phase plot. So yeah, I hope you understand that how to draw the Bode gain and phase plot. So obviously, as I'm just starting out, I am drawing very slowly. When we will solve questions, there we will understand how to do all this very fast. I'm just explaining you the concepts, so we are going slowly, step by step. Okay, So yeah, that is it for this lecture, and see you in the next lecture. Thank you for watching.